So this is the 39th session on relative velocity. In this session also we take up two numerical questions on relative velocity two-dimensional collision problems in which the relative acceleration between two moving objects is non-zero. So I'll write on the question here, okay? The first question is this. S1 and S2 are two ships which are initially situated on a straight coastline and are separated by a distance L. Ships S1 and S2 begin to move simultaneously with constant respective speeds. Constant respective speeds u and v more than u. S1 moves along a straight line perpendicular to the coastline and S2 moves such that its velocity is always directed towards S1. Find after what time the two ships meet. What time two ships meet. Okay. Is all right, all right? See one thing, in this case also the two ships finally meet at some point. This is equivalent to a two-dimensional collision problem. But here we can't apply the formula as we discussed in 34th video. In 34th video it was discussed that if two bodies collide and relative acceleration between them is zero throughout, then this equation is going to be valid. But this cannot be used here. I will just now explain it because the relative acceleration between two ships is not zero. So path of S2 with respect to S1 is not a straight line. So this formula cannot be applied here. Okay. I just clarified just now. Okay. Just draw the diagram then explain it. So see, I draw the diagram. Okay. Top view. This is a straight coastline. This is land. And here it is sea. This is a straight coastline. This is the straight coastline. Initially S1 is here, S2 is here. Separation between two ships is just equal to L. Now S1 begins to move at a constant speed u, normal to the straight coastline, and S2 moves at a constant speed v, such that at any instant of time, velocity of S2 is directed towards S1. So initially S1 was here, S2 was here. So initially S2 will move somewhat like this. After some time S1 comes here, S2 will move in here, something like this. This velocity is directed towards this S1. After some more time S1 will come here, S2 will move in something like this. S2 will come here. Okay. So path of S2 will be something like this, as seen from ground. Something like this. This is a situation at time t. At time t S1 is here. At time t S2 is here. S1 is moving at a speed of u, straight line. S2 is moving at a velocity v. Its velocity is directed towards S1 at time t. This is the distance r between the two ships at time t. Let's extend this line further. This angle is theta. Component of u along this line will be u cos theta. Component of u normal to this line will be u sin theta. And v is along this direction. R is the distance between the two ships at time small t. So now again dr by dt. R is the instantaneous separation between the two ships at time small t. So dr by dt is the time rate of separation of R. Time rate of separation of R. That is equal to rate of increase of R minus rate of decrease of R. Time rate, rate meaning time rate. Minus rate of decrease of R. Now see, rate of increase of R and rate of decrease of R will be decided solely by the component of velocities of u and v along the line joining S1 S2 along this line. So if v is along this line itself, v, this will cause the distance to decrease, and component of u along this line is u cos theta. This will cause S1 S2 distance to increase. So rate of increase of R will be equal to u cos theta, and rate of decrease of R will be equal to v. Alright. So dr equal to u cos theta dt minus v dt. Now we integrate this. That is just equal to u cos theta dt minus v dt, 0 to capital T. Capital T is the time after which the two ships meet. R is the instantaneous separation between the two ships. At time 0, R was just equal to L. And at time capital T, two ships meet. So distance between the two ships becomes 0. Now integrating and inserting limits, left side becomes minus L. Now u is constant, u comes outside the integral, but theta is not constant. Theta will keep on changing with time. So cos theta cannot come outside the integral. So cos theta stays inside the integral. So this will be u times cos theta dt 0 to t. V is constant, v comes outside the integral. Integral dt 0 to capital T minus integral cos theta dt 0 to t minus vt. Alright. Now see, still we don't know this integral. This integral has to be removed. Without removing this integral, this cannot be solved. Okay. We have to find capital T, time after which the two ships meet. Now how to remove this integral, that is the question. See, when the two ships meet, then the coordinates of the two ships will become equal. Both the coordinates will match. Okay. So what we do, we set up a convenient coordinate system. Suppose the initial location of ship S1 is taken to be the origin. This we take as the x-axis, this we take as the y-axis. Alright. This I'll rub it, okay? See, at certain instant t, the coordinates of shape S2 are x comma y at time instant t. So the two shapes meet at t barabar capital T. Okay. I'll draw the diagram somewhere here also. So I'll not have it. Okay. See. So I draw a line through S2 and parallel to x-axis. This is theta. So this angle is also theta. Corresponding angles. Velocity of shape S2 is v. Component of v along x-axis is v cos theta. That is vx. That is just v cos theta. That is the time derivative of x coordinate of shape S2 at time t. That will be written as dx by dt. We'll write in this way. So dx is equal to v cos theta dt. So now integrate this equation on both sides. Lower limit of small t is 0. Upper limit of capital T is capital T. Small t is capital T. At time 0, x coordinate of this shape S2 is what? 0, because it was situated on y axis. The lower limit of x becomes 0. At capital T, the final coordinate of x coordinate of shape S2 is x2. Okay? They just call it xf, f of final. Now v is constant, v comes outside the integral. Cos theta dt 0 to capital T. Alright? Now, at capital T, both the shapes coincide. So at capital T, the x coordinates of both the shapes become equal. At capital T, x coordinate of shape S1 will be how much? U into capital T. Because it is moving along a straight line at a constant speed u along x-axis. In time capital T, S1 will cover a distance of u into capital T. That will be the x coordinate of shape S1 at time capital T. That will also be the x coordinate of shape S2 at time capital T. So xf in this case is just equal to ut. So now I insert this integral here. So from this we get that ut is equal to v cos theta dt 0 to capital T. So this means integral over cos theta dt 0 to capital T is just equal to ut by v. So substitute this integral in this result. Minus L becomes u times integral cos theta becomes ut by v minus vt. On solving this equation, t becomes lv by v square minus u square. This is the value of t, say. Okay. So t becomes equal to how much? lv by v square minus u square. So this is the time after which the two shapes meet each other. Okay. But before proceeding to the next problem, I just explained that point why that formula cannot be used. y1 by x1 equal to u relative y by u relative x. That cannot be used here. Even though the two shapes are effectively colliding at t barabar capital T. I'll rub it, okay? See, why in this problem this cannot be used. y1 by x1 is not equal to u relative y by u relative x. See, this formula we used in 34th video. I write it, mention it here. This was discussed in the beginning of the 34th video. In the beginning of 34th video, this was discussed. See, this equation, these two are equal, equality sign holds, provided the path of S2 is with as seen from S1 is a straight path. Then only this formula is valid, otherwise it is not going to be valid. But here they see in this case, this also this in 34th video I wrote down this equation. You can refer it. Okay. U relative y by u relative x. In this it was assumed that the relative acceleration between the two colliding points, initial moment till the instant of collision, A relative, was 0. Then only it was valid. But in this case, see, acceleration of S1 with respect to ground is 0. because it moves along a straight path at a constant speed u with respect to ground. So S1G is 0. But what about AS2G? See, in ground frame, path of S2 is not a straight line, it is a curved path. So acceleration of S2G cannot be 0, it is non-zero. If an object moves along a curved path, its acceleration cannot be 0, it has to be a non-zero value. So since this is non-zero, this is 0. So relative acceleration of S2 with respect to S1 in ground frame becomes AS2G minus AS1G. This is 0, this is non-zero, so this quantity is non-zero. So this quantity is non-zero, so we cannot say that path of S2 as seen by S1 is a straight path. Therefore this equation is not going to be valid. So we cannot say that path of S2 with respect to S1 is a straight path. Path of S2 with respect to S1 is straight path, we cannot say that. This we cannot say. So this formula cannot be applied here. Okay. In the previous two videos also this formula cannot be used. I just stated it, here I have explained it. Okay. You can just remember it. Okay. This argument is valid for previous two videos also. Alright. Now I'll take up another question. Okay. I'll grab this, okay? I'll take up another question in this session, 39 session. One more question I'll take up. I'll write down the question again. S1 and S2 are two ships which are initially situated on a straight coastline by a distance L. S1 and S2 begin to move with same constant speed v. With same constant speed what? V. S1 moves along a straight line S1 moves along a straight line perpendicular to the coastline and S2 moves in such a way that its velocity is aimed towards S2. S1. After sufficiently long time, the distance between the two ships becomes constant. Between the two ships becomes constant. Find this constant distance. Find this constant distance in terms of L. Okay. It's a rabbit, okay. So I'll draw the diagram, okay? I draw the top view. This is a straight coastline. This side is land, this side is sea. S1 is located here, S2 is located here. Initial separation between the two ships is L. S1 moves along a straight path normal to the coastline at a constant speed v. S2 also moves at same constant speed v, so that its velocity is aimed towards S1. So this at certain instant t, S1 is somewhere here. As in the last question, in 30th previous question of this video, S2 will move something like this in some curved path. At time t, this S2 is here. This is moving at a speed v this way. This is also moving at a speed v. At time t, separation between the two ships is how much? Let's call it say r. Say we extend this line forward. This angle is theta. Now we write dr by dt. dr by dt meaning what? Rate of change of r with respect to time. That is rate of increase of r minus rate of decrease of r. Minus rate of decrease of r. Now we write in this way. What is rate of increase of r? See, rate of increase of r and rate of decrease of r will be decided by component of velocities of these two ships along line joining them. Now velocity of S2 is v, it is along this line, S1 S2 itself. This will cause r to decrease. And component of v along this line is v cos theta, that will cause r to increase. So rate of increase of r will be written as v cos theta, and rate of decrease of r will be written as v. So dr becomes v cos theta dt minus v dt. Now integrate this equation on both sides. Suppose after some time the distance between the two ships becomes constant. Let that time be capital T. Capital T. Here also 0 to capital T. Now initially r was just equal to L. After a long time the separation between the two ships becomes constant equal to d. So integrating the left side, integral dr L to d, it will be d minus L. D minus L. Now v is constant, v comes outside the integral. But as can be seen, theta will change with time. So cos theta is a variable quantity, time dependent quantity. They cannot be taken outside the integral. So this stays inside, but v comes outside. The integral over cos theta into dt 0 to t minus this v is constant, it comes outside. Integral dt 0 to capital T becomes t minus vt. D minus L barabar v times 0 to t cos theta into dt minus vt. Now we have to find d. Now, so question is how to find the value of d. That is the question. How to determine the value of d is the question. Fine. Alright. So now see, point is this. When will the distance between the two ships becomes constant? The distance between two ships will become constant when S2 also comes from the line of motion of S1. Because see, just say you can see this diagram. See, it's like this. S1 is going along this way, x-axis. S2 is somewhere here. At certain instant, S2 is here. S1 is moving in this way. S2 is moving this way. At certain instant, what will happen? S1 is somewhere here, and S2 also comes on this line of motion of S1. Both are moving at same speed v in same direction. In this case, the distance between the ships will become constant, d. It's a matter of everyday experience. Suppose on a straight highway, two cars are going in the same direction with same speed. Then what will happen? The distance between the two cars will not change with time. So this case also we see that S2, S1 are moving along a straight line with same constant speed v in same direction. The distance between the two ships will become constant, d. Okay. So this point has to be noted down. When distance between the two ships becomes constant, at the instant S2 comes on the line of motion of S1. After that, distance will become constant. Okay. Distance between S1 and S2 becomes constant when S2 comes on the line of motion of S1, then distance becomes constant. So that is the capital T is the time after which, starting from initial moment, after which S2 also comes on the line of motion of S1. That is capital T. Alright. Now wrap this one, okay? So now what we do, we have to find additional equation. So suppose what we do that, we again draw the initial top view diagram. This is the straight coastline. This is the origin of coordinate system. This is taken to be the x-axis. This is taken to be y-axis top view. Initially S1 was here, S2 is here. At time 0, at t block capital T, S2 comes here. At t block capital T, S1 comes here. At t block capital T. Both are moving in same direction with same constant speed v. The distance between the two ships becomes constant equal to d. Okay. So now see, at this instant, x coordinate of ship S1 x1 is how much? Vt. Initially S1 was here. In capital T time S1 comes here. This distance is equal to how much? Speed into time. Constant speed, so it's moving. And x2. What is the x coordinate of ship S2? This distance is d. This distance is how much? Vt. So this distance is just how much? X2 is how much? Vt minus d. Vt minus d is the x coordinate of S2 when it comes on the line of motion of S1. This distance is x2, Vt minus d. Now only one thing we have to find x2. I'll just redraw the diagram again. See like this, see. For example, at time small t S1 is here. And at time small t S2 is somewhere here. This is theta. This is also V. I draw a line through S2 and parallel to this line, theta. This component along this line is V cos theta. T time for coordinates of x and y are x comma y. This is the x component of velocity of ship S2 at time t. Vx is nothing but dx by dt. Vx is equal to V cos theta. Dx becomes V cos theta into dt. Integral over V cos theta into dt, 0 to capital T. Initial x coordinate of ship S2 is 0. And finally when S2 comes here at t over capital T, x coordinate becomes Vt minus what? D. Alright, fine. I'll rub this one, okay? So what equation I get? Integrate left side. What do I get? I get Vt minus d barabar. V comes outside the integral. V is constant, but cos theta remains inside because it is a function of time. Okay. So now these two integrals I eliminate. So this integral I eliminate this one. So from this equation we see that d minus L equal to V times this integral will be equal to this integral Vt minus d by V minus Vt. So d minus L V by V goes away, Vt minus d minus what? Vt. Vt goes away. So 2d barabar L. D barabar L by 2. This is therefore the required answer. Alright. So d is equal to just how much? L by 2. So when the distance between the two ships becomes constant, that is just equal to L by 2. Alright. This is the required answer. Fine. So this was the 39th video on relative velocity. I'll take up one or two more videos on relative velocity on this topic, on two-dimensional relative velocity collision problems. And then I'll pass over to the relative velocity problems in translating frames. Okay. For that will be around 12 videos. So in total I think around 50 to 55 videos on relative velocity for JEE Mains Advanced and NEET level. Alright. You can go through them. If you go through them, you understand it very clearly, it's going to be very helpful. If you once going through these problems, if you try to solve some of the problems from some of the books, then you will solve most of them. There's no doubt about it. Fine. I close it here. Alright.